Hello, this is our last part of the video series about regression for nonlinear data. We've looked at power functions and exponential functions, and now we're going to look at polynomials. We'll talk about quadratics first. And a quadratic, of course, is something of the form ax squared plus bx plus c. And we're looking for the best choices for a, b, and c that will fit a quadratic to a set of data where we will minimize the sum of the squared error. And as we've seen before, what that basically means is we're taking the partial of v with respect to a should equal the partial of b with respect to b, should equal the partial of e with respect to c, should all equal 0. And we want to solve for a, b, and c. Now, we'll leave that as an exercise to work out those details. But one thing you'll find that's different about this example from the last two that we've seen in this section is that this actually does yield a solution that can be found algebraically. So we don't need to resort to transformations. And what that means is we don't need to resort to semi-log or log-log paper or other methods to get a good fit. Whatever the traditional algorithm gives, we know is correct, and we can have confidence in what a spreadsheet provides. Now, there are still a few pitfalls we need to be aware of. First of all, notice those other models had 2 parameters, and now we have 3. So 3 parameters is always going to give, generally speaking, a better fit than 1 or 2. So we shouldn't be surprised if the r squared value increases. In fact, as a general rule, r squared is going to increase as the number of parameters increases. So imagine a cubic or a quadratic, quintic, and so forth. Those are going to be even better fits. And that doesn't necessarily mean you have a better model, because you could be overfitting. So beware of overfitting as the degree increases. Because as your polynomial degree increases, so does your number of parameters, of course. So that's one thing to be aware of. The other thing to be aware of is that a spreadsheet typically can provide the least squares fit for degrees 2 through 6. And honestly, for most data sets where we're trying to find some sort of trend, it would be unlikely that a degree of more than 3 or 4 would be a good choice anyway, but that's the option. But there are certain situations where a higher order polynomial might make sense. And in that case, a spreadsheet won't work, but other tools like a computer algebra system will. And we'll have a whole nother section dedicated to that. So for higher order polynomials, just hang tight. And we'll see that in the next section. Let's just see, though, how this looks for our data sets that we looked in the last couple of examples, and see how a quadratic fit might have helped or hurt as we analyze those previous 2 data sets. So let's go to the spreadsheet now. So here we have our planetary data, and we've already calculated the power function model and the corresponding SSE. And from Kepler's law, we expect this to be the so-called right answer. And notice the squared error does add up to a pretty big number, but when we look at how big the y values are, that's actually not so bad. So let's see how it would change, though, if we went for say, a quadratic fit. So the good news is I can go to my trend line, and the spreadsheet gives a polynomial option, and then here to the right, you can pick what order you want. We're just going to stick with order 2. And we still want to see the equation of the r squared value. Notice we get a great r squared value. But again, that's not necessarily a surprise. But maybe the fact that both a power function and a parabola do so well is interesting. And so now let's see how our squared error compares. Because keep in mind, these algorithms that minimize squared error are only for the particular function we're interested in. So even though this power function might be the best power function, this is the best quadratic, who's to say which one is better overall until we test it out? Actually, when we look at that model, we see that it has a negative y-intercept, which doesn't really make a lot of sense. So one thing we might want to do to fix that is we can come down here, and there's an option to set the intercept to 0. And so now we get a little nicer, at least more sensible model. So that changed that first coefficient to 0.0019, and the next one to 5.1536. All right, so now we can drag that down. Okay, so here's the prediction for the model. So first order of business is let's take a look and see how individually the model compares to the actual and versus the plot. Because if our model doesn't match the plot, then we might have either typed something in wrong or we didn't get enough decimal places from the spreadsheet answer. So for instance, this point here, it looks like it's around 30,000, a little bit below the dot. And when I look at this, I see, yeah, a little below 20,000, a little bit below the actual dot. That looks encouraging. This one looks pretty close, 61,000, 60,000. Yeah, so overall, not too far off from the line. If I want to do the squared error, and just like before, I'm going to do this. Prediction minus the actual. I'm going to square that number. And we don't need the decimal places. And then we need to add all that up. And notice we get, going on 4 million versus 160,000. So clearly this model is a lot worse, even though visually it looks pretty good. But even comparing like number of Earth days really isn't that great of a fit. So we can definitely say the power function is better. What about US population? This one, the exponential had a nice fit, but it didn't extrapolate so well. So let's try a quadratic for this one as well. Go to trend line polynomial, going to stay with order 2. I don't need a 0 intercept, so I'm okay with an intercept of 4.1. That seems reasonable. Getting a great R squared value. So let's give this a try. So our quad model is 0.0044 times that squared plus 0.0476 times that plus 4.1676 plus 4.1676. So we'll drag this down, get rid of those extra decimal places. Again, visually for the data we have, looks great. For extrapolation purposes, 1870, they're all in the same ballpark. For 1900, 76 million versus 63 million. Maybe that's a little better than other ones. 1950, 124 million versus 150 million. So that's actually a lot better than our exponential models. And then in the year 2000, 208 million is certainly a lot better than 2 billion. However, we can be concerned that that's still not a great fit, and so quadratic probably isn't a perfect model either, but at least it might have a little more value and maybe some short-term extrapolation, and interpolation it might be a wash with the exponential. You can calculate the squared error, but again, if you look at the numbers are so close for the actual data values that the squared error is probably not going to be that different, probably not going to be enough to make us choose one model or the other just for the SSE. But you can try that on your own if you want. So that's a couple of examples using polynomials. When we get into more higher order situations, we'll check that out in the next section, and we'll see you there.